Good morning, everyone. Can you hear me? Yep, great. So I'm Nikko Strom. That's me on that slide. And there's some contact information at the bottom. I've been with the Alexa team for over 5 years now, since it started. It's been a great ride. So today I'm going to talk a little bit about the deep learning technologies that we have in Alexa. So I'll start with just some background on Alexa itself, and then I'll talk about how we apply deep learning at scale with all of the massive amount of data we get. And then I get into some details about the speech recognition and speech synthesis, which are two of the areas where we apply deep learning. This is not going to be a super deep technical talk, so if that's what you're looking for, you're probably going to be much more happy in the afternoon session. There's going to be deeper talk then. And then finally, at the end, I'll talk about some of the programs we have with our partners in academia and industry. So it started about a couple of years ago when we released the first version of Amazon Echo. We started small. It was a limited release. We wanted to see how users used it before we had our general availability. It was pretty clear pretty early that people liked it, so we earlier than planned, we started selling it to anyone who wanted it, and ever since then we've sold millions of these devices. People like this thing, and it's interesting. I'll talk about that more, but it's interesting how that is different now from when earlier. Like Lee Deng said, I also worked on these earlier systems, and they didn't really have any commercial impact. But anyway, so we've expanded this to a smaller version, the Echo Dot, and another wireless version. By the way, you can try all these out at our desk after the coffee break if you want. And then I guess for the Christmas season last year, we added white version also. Same thing, but white. So it's not just those devices, though. Here is the Alexa again. It's our device. We built this. But we've also put this on the Fire TV device, and you can now get it on the Fire tablets. And there's also third-party devices that have Alexa built in. So there's a Alexa voice services program that lets you integrate with an API into Alexa services. Even watches, actually. I actually have one of these watches. It's fun to talk to your watch. So those are all the devices that have Alexa built in. There's also a whole bunch of home automation devices that don't really have integration with voice directly, but they tie into Alexa, so you can use Alexa to control them. My favorite is the light switches. I have light switches in my home. All my light switches are smart, so I can say things like, Alexa, turn on the kitchen light. Sometimes it's silly because you're right next to the switch, but there's other there's other uses for this. Like when I go to bed at night, I can say turn off all the lights upstairs and things like that. It's fun, and I have a special setting for watching TV, so I can say Alexa, turn on the TV mode, and say you have to be there. Anyway, so another way that we expand Alexa is through skills. And I don't know if you see in the news, but we reached a milestone recently. There's now over 10,000 skills for Alexa that you can enable. And what a skill is an experience for Alexa that third parties can develop. So we don't develop these. There's an API for third-party developers to add their experience to Alexa. So all of these things that make Alexa great and expanding all the time, it means that we get lots of data. So like I said, we've sold millions of these devices. They're used for all kinds of things. Sometimes we don't even know because 10,000 skills, I can't keep track of all the things that people use it for. And one of the things about this era Lee talked about, is that people actually like using these. So I've been in the industry for a long time, and I worked on telephony systems, and people don't really like to use that, right? So it's kind of not very thankful to be working on that. But for this, people like using it. We get emails from people who love it, and it's getting really high ratings on the Amazon website and all that. So that means that these devices are being used a lot. Like there's millions of them out there, and they're being used every day. So we get a ton of data, and so we need to learn from that data with machine learning, and that presents a big challenge for learning at scale. Just for learning at scale, I have a longer form talk that I did at the AWS reInvent last year. So it has the same title as this talk, so if you want to find that on YouTube, you can look it up. The way that I think about data in speech and amounts of data is in hours. So, right, so in the US, you have to be 16 years of age to drive one of these, right? That was on the top of my mind when I made this slide, because my daughter is not driving, which is terrifying. But 16 years is 140,000 hours total. So you probably don't hear speech all the time. So let's say you hear speech 10% of the time. So, sometimes you're driving, or you're sleeping, and so on. So let's say 10%. So maybe when you're 16 years old, you've heard 14,000 hours of speech. That's all the speech that you've heard, and a 16-year-old is very proficient in language, right? So that's their training data. That's how they learn speech. So I'm going to use that number to compare with what we're using for our machine learning systems. Anyway, so we have all these data. We have thousands of hours stored data from our customers in S3. And we train these models on AWS EC2 instances. Because it's so much data, we have to do distributed training, so we use many GPUs in parallel. And this is where the challenges start. So here, for example, this slide is kind of old. It says I was using G2 instances. We have much better, faster GPUs in AWS now. But so here we're talking about 80 different GPUs working together to train a model. The problem with that is that all these GPUs have to communicate with each other, and the way this training works is that every GPU has to send their information to every other GPU, and they're super fast at computing these. They compute model updates super fast, maybe many updates per second, and each update is nominally it could be hundreds of megabytes. So you pretty quickly reach a bottleneck for I/O between all these GPUs needing to communicate. So that makes it hard to scale this training. So you can solve this problem in a couple of different ways. What we did at Amazon, we figured out a clever way to compress these updates and make approximations to make them several orders of magnitude smaller, and that's how we can do this. Here's a graph from a paper we published a couple years ago. The principle is the same still, but it's even faster now. So here, what you can see here on the x-axis is the number of workers that we applied to the problem, and on the y-axis is how fast they can process speech. So you can see that we used up to 80 nodes in this case, and if you look at that, what's important here is that the line is almost straight. It means that as you use more and more GPU resources, you train faster and faster in sort of a linear way. It doesn't saturate that much. A little interesting factoid here is that upper right, where we use 80 GPU nodes, and so we could process about 550,000 frames per second. So to translate that to you, that's about 30 minutes. So what that means is that in 1 second, we could process 30 minutes of speech. So, and this is when I want you to think back at this poor 16-year-old that can process a couple of hours per day, perhaps. And so that 14,000 hours of speech that she had heard at 16 years of age, we can process that in a day or less. Right? So So Microsoft did a great job with a superhuman speech recognition paper. But if you think about it, we should be superhuman because we have all these resources that humans don't. Right? We can process 14,000 hours of speech over and over many times in a week, whereas it takes 16 years for my daughter. Anyway, so that sets me up for the speech recognition. By the way, speech recognition is where it all starts, right? So if speech recognition doesn't work, then the system doesn't work. So it's super important, and that is probably one of the reasons why there's many things have come together recently, but speech recognition has gotten much better because of deep learning, and so that's one of the reasons why there's a much greater acceptance for these types of services. So here's a standard vanilla type of speech recognition pipeline. You get some sound wave into the system, you do some signal processing. Out of the signal processing comes a feature vector. That's, let's say, every 10 milliseconds, there's a vector of numbers that describe that part of the speech. The next module is an important one. That's the acoustic model. It takes it's a classifier that takes these feature vectors, and for each 10 milliseconds, it's trying to classify what's the probability of each of the phonetic symbols for that little slice of speech. The third one is also important. It's a big, huge search over all the possible pronunciations and all the possible phrases with their likelihoods. So it's a search that takes these phonetic probabilities as input and finds the most likely word sequences output. In this case, it was probably a thermostat skill on Alexa increased to 70 degrees. That's like a reasonable thing to do. And then usually there's a last step which kind of just normalizes the text to something that looks better. All of these modules we use machine learning and deep learning in all of these modules in one way or another. Today I'm going to talk a little bit more about this one. It's a good example of probably the first example in speech recognition of using deep learning. It's a classifier that takes feature vectors as input and phonetic probabilities come out. It's a nice constraint problem. There are many things I can talk about that, but I'm going to pick one and an interesting one. So I'm going to talk about a deep neural network for acoustic modeling, and here's the gives you an idea what the network is. It takes input at the bottom, and then there's a number of hidden layers in the network that transform the feature vector, and at the end there's the last layer of the network that will output the phonetic symbols. Right? In this case, US English was the one we started with for Alexa. So the phonetic symbols are for US English, and we have thousands and thousands of hours, so we have a pretty good model here, even though Amazon Echo is a far-field device, which makes it harder. We get pretty good speech recognition accuracy from this. Now, last year we expanded to German. So what do? Obviously, we don't have quite as much data for German. So what do? Well, so we use this method called transfer learning, which is something that was hard to do with older techniques, but it's pretty easy now to do with deep learning methods. What you do is you just keep everything the same, but you remove that last layer that has the final output, and then you add another last layer for German. Completely different output phonemes. German has different phonemes and so on, but everything else is the same. And then we use that as a starting point, and we train with whatever little data we have for German. And it turns out that gives you a much better system than if you would only had started from scratch with the German data. All right, so the next thing I'm going to talk about in speech recognition in particular is the cocktail party problem. This is so Alexa, like I said, is a far-field device. There could be many people in the room. There's a wake word, so probably it's not that hard for Alexa to point there. So Alexa has this microphone array, so it can start listening in a certain direction to some degree. And so when someone says Alexa, that's a pretty strong cue that, okay, so I should listen in that direction. So the starting point is kind of not that hard, but then what happens next is that now it looks all the same from all the directions, right? It's much harder because it's open-ended. The user now said play some jazz. They could have said something else, and someone near that person could say something similar, and they could keep talking. The hardest problem here was that we don't really know when they stop talking, because there could be someone else standing next to them, keep talking. We don't know when we should stop and start processing that other way. So the way we solved this was with something we call anchored speech detection. So remember, the problem is, how do we know when this particular speaker stopped talking? And even though there's other people very close to them that are still talking. So when we do this is we use the Alexa word, which is kind of well-defined, and we use that as the anchor word. And then we look for speech that is consistent with that anchor word, because it's the same speaker, right? In deep learning lingo, we can use an encoder for the first part, for the Alexa, and then a decoder for the second part. I will show you a little bit more detail here on this slide. So here you can see that there's an LSTM. It's a recurrent neural network that's processing the first part, the wake word, Alexa. And out of that comes an embedding. It's just a vector that describes that speaker's voice characteristics. And then for the second part, when you recognize play some jazz, and we're trying to detect when they're done speaking, we use that anchor to condition the decision. So we still have the input from the actual audio, but we condition that by the anchor embedding, which tells us, here's how you should listen for that particular speaker. By the way, so I don't go into a lot of detail, but maybe you notice that I put our published papers on the slides. So for those of you who are taking pictures, you can look at them later. Or I don't know if these slides are going to be published, but if you want more detail, you can ask me later. The second area that I'm going to talk about today is speech synthesis. Now we use deep learning for many other things too, natural language understanding and so on, but today I'm focusing on speech recognition and speech synthesis. We think Alexa sounds very natural and very good, and we're investing a lot in speech recognition, speech synthesis. I'll start by just give you an overview of what the problem is. So you have some text. Here's what we want Alexa to say. Then you normalize, and this is kind of the opposite of what the last step of the speech recognition was. Right? We take this written text and we make it into words. So it's only the words and not the dollar sign or anything like that. The next step is to go to the phonemes. So there's a basically, usually this is a rule-based system that takes words and spits out what the phonemes are. It's mostly based on the actual pronunciation lexicon of these words. So now we have the phonemes, and now you can't read it anymore, but the system will need this. And the next step is the hardest one, is to transform this to actual waveform audio.
She has $20 in her pocket.
Wow, that works. Oh, okay, good. So, and that's how Alexa would say it. Right? So I'm going to talk just a little bit about how this works. So most of these high-end systems are using concatenative synthesis, which is works this way. You take a professional voice talent, you record his or her voice, and you create a large database with short segments of speech from that person. And then you annotate those short segments with all the information you have about them. What's the pitch? What's the duration? Which word did it come from? What is the phonetic symbol? And so on. Right? And then you take your current phonetics sequence that you have that you want to speak, and you try to search this database for the best possible match to stitch together all these sequences to sound like someone actually saying this. This is an old technology. It's been around for a long time. The new thing I want to talk about here is how we actually use deep learning to select these. and the way to think about it is that you have the phonemes and the words that you want to say, and then you want to find targets for these annotations in the database. So if I say for this phoneme in this context, I want to have 120 hertz pitch, and I want 50 millisecond duration, and so on. And then you go and search the database for that type of segment, and you use that for your final synthesis. Where we use deep learning for this was to make it more natural sounding, make the prosody, the phrasing, and the pitch sound more natural. And so what we did, we took a bidirectional recurrent network, also an LSTM type network, and we fed it with all these information we have about the word that we want to say. The phonetic features, the linguistic features, semantic word vectors is a vector representation of the word we want to say, and so on. And the network would then output these three quantities: pitch, duration, and intensity. And then we go search the database for that. This becomes one of the things we use to search the database for the right segment to speak. This is mostly important for long form reading. For short form, it doesn't matter as much if you get some phrasing wrong. But for long form, you can usually hear a difference. Can you make it a little louder than last time? So I'm going to play some examples, and you have to listen carefully, because our baseline system was already pretty good. But I think if you listen carefully, you can see how the deep learning system, which is the after version, will sound flow a little bit better. So let's see if this works.
Over a lunch of Diet Cokes and lobster salad one balmy fall day in Boston, Joseph Martin, the genial, white-haired, former dean of Harvard Medical School, told me how many hours of pain education Harvard med students get during 4 years of medical school.
All right, so you could hear that. That sounds pretty good, but it's not. There's some things that doesn't flow right. And here's after, and listen carefully, because this is also not perfect, but it's better.
Over a lunch of Diet Cokes and lobster salad one balmy fall day in Boston, Joseph Martin, the genial, white-haired, former dean of Harvard Medical School, told me how many hours of pain education Harvard med students get during 4 years of medical school.
So I'm Swedish, so I don't hear all the nuances, but I think it sounds quite a bit better. Finally, those were all the technical things I wanted to talk about. I want to finally talk a little bit about some of our collaborative programs that we do with our partners in academia and industry. The first one is pretty cool, I think. This is Alexa Prize. I don't know if you've heard about this, but it's a competition. So we funded, I believe, 12 different teams in academia all over the world to build a social bot. This is meant to be a bot that you can talk to, just like you would talk to a person about current events or something. And the goal is to actually keep that discussion on for 20 minutes. So it's a super hard problem, and we don't think we can solve this all on our own. So we funded these expert teams in academia to try to solve this problem. It's an annual prize, and there's a grand prize. The bar is very high for the grand prize. Basically, the bar is that you should be passing for a human, essentially. But every year the winner gets an annual prize as well. Probably a really cool part about this, I think, is that look for this later in the year, but I think we will actually release this as a skill for Alexa, so you can try this out yourself if you have an Echo, and you can rate these. I believe they're going to do it so that you don't know which team you're talking to, and then you can rate it, and then we can see who gets the best ratings. But look out for that later in the year. That'll be really fun. The next one is the Alexa Fund. It's a venture fund that invests in startups and entrepreneurs that want to expand the Alexa ecosystem or Alexa services. Let's see. I think most of the investment so far has been in hardware, but I believe they look at both software, that would be skills, and hardware as well. And the last one I want to talk about is an extension of this, which is the Accelerator, which we do together with Techstars. And if you're interested in that, the AlexaAccelerator.com down there is where you want to go, and then those are the dates. And that's all I wanted to say today. Thank you so much. Sure.
Do you guys consider using like adversarial networks to make speech synthesis?
Have you guys considered using adversarial networks for speech synthesis? So we have a speech science team in Cambridge and in Poland. It's distributed. So our main speech synthesis team is in Poland, and there are also scientists in Cambridge, UK. They are looking at all kinds of new innovative ways of improving speech synthesis. Obviously, on everyone's mind right now is the Wavenet paper. Was very interesting. Not super practical because it was taking too much compute and taking too much time to get things working. But adversarial networks are interesting because they're good for. It's a good paradigm for generating any output signal. So it's one of the things that they're looking at. They're looking at several different deep learning methods.
Hello, got a question about the speech synthesis. What do you think about Google's Wavenet? Is it the right way to go, or you think the traditional way is the way to go?
Sorry, Google what?
Wavenet.
Oh. So Wavenet, that was the one I mentioned just now, right? The speech synthesis one. I think it's very interesting. It's exciting that they were able to do this. It's what they did is not quite practical for us because it's too slow. Like I don't know exactly how slow, but I heard that it takes several hours for 1 second of speech to. So our customers don't want to wait that long, but it's very interesting.
But with the increasing compute power, definitely the speed will be dramatically increased, right? So what do you think? Is it the right direction we should explore, or?
Like I said, we have I'm not in that team, but we have speech scientists doing synthesis research in Cambridge and in Poland, and they're looking at all these things. Ultimately, for us, it's all about making the voice as natural as possible, making it more expressive, maybe express feelings and so on. So they focus on that first. That sort of what we always do at Amazon, we work out backwards from the customer. So what does the customer want, and then we look at what technologies we want to develop.
Hello. I'm here. Thanks for the great talk. So my question is, can Alexa sense or capture the emotion in the sentence right now, and what's the plan for the emotion part? Thanks.
For emotion, so Alexa cannot capture your emotion in your speech right now. It can capture indirectly by if you say something, the meaning of what you say can be emotional too, right? It will recognize your curse words, for example. But there's no, like the tone of your voice, we're not able to use that yet. Again, we have over 100 scientists working on Alexa on speech in general. So all of these areas we have scientists working on, in different intensity, but we don't have anything to announce about this, but it's things that we're working on for sure.
Thanks.
Hi. Here. Hi.
There.
Hi.
Thanks for a great speech, and I really like the product and how it may influence our life in the future. My question is, rumor are saying you guys are recruiting 10,000 more engineers in the whole Amazon in the next 6 months. Right or wrong? Thanks.
I think there's a booth in the back, there's a table in the back with Amazon recruiting, and they could probably answer that question better than I can.
Hi, my name is Mike Kata. I'm curious more about the aspects of security and privacy, since I understand that Alexa is listening all the time, and with the most recent revelations about how the CIA and others are trying to get into all the systems.
This is a question that come up all the time, and it's a super important question. And so one thing that is not always in articles that are written about this, one thing is that the device is listening all the time, except of course if you have the mute button pressed, then it's not listening at all. It's a hardwired electronic switch that the microphones are completely off if you press the mute button and it turns red and the ring turns red. Now what people don't always get in these articles is that it's listening for your wake word all the time on the device. That's not ever stored though, so it's only listening for the wake word. It's only when the blue ring starts spinning or pointing at you, that's when Alexa has heard the wake word and it starts recording you. So only the thing that you say after the wake word is ever recorded. And if there's a false accept of the wake word, it happens to accidentally recognize the wake word, it's only when the blue ring is on, that's when it's recording. And even in many cases, even if the blue ring goes on and you didn't actually say anything to Alexa, it'll immediately go off again. And that means that we sent some stuff to the cloud, we realize this is not for us, and then we don't store it. So when you say it's listening all the time, it's correct technically. The microphones are on all the time, unless they're muted, but nothing actually gets recorded.
My name is Edward, and I'm also from Amazon. Here.
Where are you?
Yeah. And my question is, when it comes to large-scale system, what is the advantage of deep learning Alexa module compared with traditional shallow module?
I didn't get to talk a lot about the skills, but skills are, so Li Deng talked a lot about the open versus closed system. Skills are super exciting, but they're also a big challenge for us because there's many of them, and we don't build them ourselves, right? So we can't really control what's going on in the skills. So it makes this open dialogue problem even harder because our central system will have to adapt to whatever third-party developers do. So I think the question was about deep learning. Skill developers don't necessarily need to know about deep learning. What the APIs are at a much higher level. You specify the experience that you want the user to have. We are using deep learning behind the scenes to decide what skill to use and to do the natural language understanding, to fill the slots that your skill needs, and so on. And this is an area of pretty intense activity right now for us.
Hi, question about data collection.
Last question.
Right. So now that Alexa is widely deployed, are you able to crowdsource training data for Alexa through everyday usership?
Training data from this is the most important source of training data for us. So when you're using Alexa, and that's when the blue ring is on and we are recording you, that data we're using to train our models. We have, and when you say crowdsourcing, I want to be clear that there's no one outside of Amazon that can listen to that, but there are a team of data transcribers that listen to it and write down what the correct words were so that we can train our systems on that.
Okay, I hope I have a last question. Nikko, that's the top. Have you guys started using MXNet to train your stuff?
So MXNet, the question is interesting because MXNet has been endorsed by AWS, and they're pouring a lot of resources in MXNet and making it easy for everyone to use MXNet on AWS, right, on EC2. Alexa is older than MXNet, so we are using something else still that we developed before MXNet. We are looking at other frameworks as well, but right now, and I should say these frameworks are, people talk a lot about these frameworks, but it's really the libraries beneath them that are the most interesting, like the convolution implementation, for example. We all use the same. It comes from NVIDIA. So we're using a different framework, but we're looking at all these other ones. And frankly, some of our scientists are using TensorFlow, MXNet. They can use whatever they want for their research.